Atmospheric circulation is responsible for the majority of latitudinal energy transfers at the global scale. But close behind are the oceans, and the oceans have unique properties that alter the functioning of ecosystems in ways not predicted by an understanding of atmospheric circulation alone. The authors state that, like the atmosphere, the ocean maintains rather stable layers with limited vertical mixing between them, and this is a key property of the oceans. In these layers are currents, and ocean currents move a lot of energy. So we take a look again at figure 2.7. You can see the patterns of radiation gain and radiation loss, and this difference here are driven by atmospheric and oceanic energy transfers. The patterns of oceanic and atmospheric energy transfers near the equator are pretty similar. As you move further north or further south, the atmosphere moves a lot more energy than the oceans does. But still, there are large quantities of energy that are moved by the oceans in both the northern hemisphere and the southern hemisphere. And these, like atmospheric circulation, impact climate. In part, what we see with the oceans are large energy gradients that get set up. In addition, we also have salinity gradients that have both vertical and horizontal components to the circulation. What's important to know is when you're thinking about oceanic circulation is that dense water tends to sink. And water becomes dense when it's colder, up to a certain point, 4 degrees Celsius, or saltier. Salty water sinks compared to more fresh water. Together, differences in temperature and salinity generate what's called thermohaline circulation, which are the major circulation patterns in the ocean. As an example, the authors show patterns of both temperature and salinity that you would find in surface waters versus more intermediate waters. These surface layers happen at about 100 to 200 meters in depth. You can see that the surface waters tend to have low salinity and higher temperature. But once you reach a certain point, the temperatures decline and the saltiness increases. This rapid change in temperature is known as the thermocline, and the rapid change in salinity is known as the halocline. These differences that we see regionally in both temperature and salinity generate planetary scale circulation of ocean waters. Here's a three-dimensional view of the major currents that we see in ocean water. Here's the Pacific Ocean, and you can see down deep in the southern hemisphere are cold, salty, deep currents, and they upwell off the coast, off the eastern coast of Asia. Here, they start to go through the Pacific and back around south of Asia, Africa, and back up into the North Atlantic. When they reach this point, they tend to cool off and also become more saltier, and that's where they sink, going back down deeper and continuing the circulation pattern. So we have cold, salty, deep currents that upwell and warm, shallow currents that run along the surface until they eventually decline also. Viewed from above, here are the warm and the cold currents again. These are the cold, deep currents here that move along the bottom of the ocean and upwell, typically in different spots along the globe. These waters warm and then move along the surface in this pattern again till they eventually decline. And again, these are driven by differences in temperature and in saltiness. These patterns of circulation of the oceans transfer massive amounts of energy. Here's a satellite image that shows differences in temperatures of one of the major circulation patterns, the Gulf Stream. And you can see relatively warm water that's moving north and also to the east. And then cold water patterns that show up here off the eastern coast of Canada. This, as you remember, are the major areas of downwelling of cold water too. And this is the warm water that's shifting over before it's eventually going to swing back to the west and begin to descend. In addition to the thermohaline circulation, there's also additional ocean currents that are really important. In part, these ocean currents are not necessarily driven by differences in temperature and salinity, but also by the prevailing winds. Here's a map of some of the major oceanic currents that we have. So for example, we just showed a picture of the Gulf Stream that comes off the Gulf of Mexico, the eastern coast of the US, and into the North Atlantic. This North Atlantic drift continues some of the Gulf Stream and brings large amounts of heat into northern Europe and makes the climate there much milder. In contrast, the Humboldt current is a cold current, and that works its way along the western part of South America. And because these waters are cold, they evaporate a lot less water, and these areas are much drier than you would have expected based on their latitude alone. So, ocean currents move a lot of energy, and they play critical roles in determining the distribution of different kinds of ecosystems across the globe. They make land warmer, where warm currents move along it, and colder. In addition, they change the precipitation patterns. Where warm currents are, you tend to have a lot more precipitation than you would expect. Where colder currents are, they tend to be a lot drier. Lastly, it's really important to understand ocean currents for terrestrial climate. And when we start to take a look at the regional patterns of climate and the regional distributions of different ecosystems, they're in part going to be driven by the oceanic currents in the neighboring waters.